my left button on the keyboard on the mouse doesn't work anymore. So it didn't have enough safety factor on it. So yesterday, Professor Eager gave you more examples that, to some extent, are industry-specific. When NASA and aerospace people go and design something, if we go back to what we said about the statistics, in principle, there are not that many people involved. It's the pilot and the crew, and unless the debris hit the ground on a populated area, it's a small number of people involved. Now, it does involve the news people, and there are other bad things associated with having a failure. But as far as this little criteria, I'm going to go back to it right now so we know what we're talking about. When we talked about this, how willing we are to accept a failure, we don't have here aerospace structures, but they'll have a lower safety factor probably than towers and masts, or they'll be in the same area. So we're looking at, we're about 1,000 times more willing to accept a failure just based on the number of people. There are other criteria than we are if we're looking at a dam or something that would affect the whole population of a town or a city. And like the pressure vessel example is one. When we had the molasses disaster in Boston a very long time ago, I don't think that led to a boiler and pressure vessel code, but it led people to realize we can't have structures that are storing large quantities of liquid in a city without having any control over how it's designed, how strong it is, and what would happen if it fails. So it's clear to us already that depending in which industry you're working or you're designing a product for, that you'll use a different design approach, and the numerical value of the factor of safety will be different. So we'll wrap up today, and I decided to go on with two more examples. One is an aircraft design example. The other one is a roof joist design. So they're very different industries. Both are governed by codes and standards to a large extent. We've covered enough, I think, when I talked about ATVs, when I talked about my trailer. We covered examples of products that the designer or the manufacturer has a lot of flexibility on how they will make the design and how they're going to validate it. So in today's lecture, it's a little bit more prescriptive, and we're going to be looking at two different industries. So let's go with that. For the aircraft example, I want to talk about the front flap of an aircraft wing. So I worked in small aircraft. They were building the original jets. So when you take a shuttle from here to DC or from here to Cleveland, the shuttle type aircrafts for 70 passengers up to 90 passengers now will have this design where most of the time the engine is not going to be right here. It's actually going to be close to the tail in the back, and that makes the wings a little smaller. So it's a very, very narrow and elongated design. You still need, even when your wings are smaller, you're more dependent on them. So you don't want them to be covered with ice when you're going through a transition in weather. So they have this heating system for the leading edge of the wing. When you take off on a storm, you've probably seen they have firefighter type of jets to heat up the fuselage so you don't risk it. It helps also against de-icing, but for a critical component like the front here, this geometry has a lot of effect on aerodynamic. When you pull it out you know, if it's twice as heavy, the safety factor on all the arm that's holding it out. Because what happens with the front of the wing is for takeoff and landing, you pull it out so you have more support, and you create a turbulence under the wing to help with keeping the airplane up in the air. So you need all of that to work in the same condition, even if you're going through a blizzard or an ice storm. So this big hole that we have here is for air circulation. So they recirculate hot air from the engine back into the wings to keep it warm. And the system to do that is a little complicated, because you can't go and set very precisely what's going to be the temperature of the air that's going to come off the engine. You can have some control over that, but there's only there's a window of opportunity to collect that air, and it's typically hot. So you need to go through a certain design process where you say, well, you know, my air temperature is going to be between so much and so much. And then you can control the heating by the volume of air that you're going to blow through the wing. That's okay. But the temperature of the air that the metal here is going to see will vary. And so when I worked in that aircraft company, they had these PhD guys that were putting sensors and sending the thing up in the air, running it to have some idea of the temperature. But they never really came up with, this is the maximum value. It's never going to see any higher temperature than that. So they had a lot of variation. And given that, it was very hard from a design standpoint to say, we're going to go with aluminum. You could easily get to temperature where you get a softening of a heat-treated aluminum. So say above 200 centigrade for an extended period of time. And we don't really know the extent of the period of time. So for the primary structure, so what is painted in green here, the design that was certified already with the FAA and the Canadian equivalent was titanium, because it's able to take higher temperatures. You know, it's resistant to corrosion. There's definitely a stiffness mismatch between the titanium rib here and the aluminum skin. So why on the aluminum we say, okay, let's live with it? There are a couple of factors. One is you always have the cooling from the outside. So it's always going to be touching the storm air, and therefore it will be cooler. And also, really, if the surface of the wing got a little softer, first of all, it'd be a way to figure it out. If you have a crack on the exterior fuselage, you can see it. When it's on the interior, here we have the benefit of looking at a cut piece. This was a test piece. But in reality, this wing is long, and you don't see all the ribs. So you don't see all the green pieces. So when we're talking about an acceptance criteria for a crack length, well, it would have to be a very long crack. It would probably have to be a fail-safe way of designing if you were to go and say, well, I'm going to allow this component to crack. So the way it was working out was essentially this should not be cracked, or if it's cracked, it should not grow to a significant length within the life, the surface life of that wing component, which is always, you know, limited by a number of factors, and then you have to take it apart and really inspect it, because it's not easy to inspect it on a day-to-day basis. So say that was a design that was about 10 years old by the time I was there, and it obviously took maybe 5 years to certify it. So it had been produced for about 5 years, and they were getting into this reconsideration stage. They wanted to be competitive. This was a Canadian company. They wanted to be competitive with the Brazilian for the same market. So they had to start looking at their cost. They were kind of in the first round they say, well, we want to pass the FAA. We don't want to go through all the details. We got to be done with this. It's going to take 5 years. If we try to optimize everything, it's going to take longer. So they went on and picked that aluminum component as a wrought plate, 3.5 inch thick, a slab essentially of titanium, and that's what they were using to machine out this detailed rib structure that had only about 1/8 of an inch of thickness in the center. So if we look at it in a cross section, this is pretty much an I shape. So you have the top surface, you have the web here in the middle, and the web at some location even had a hole in it. Then you have the other surface that's contacting with the wing. So one of the reasons for having this large of a surface is for stiffness, but it's also providing for fastening the skin. So say we have the skin here, the lower skin riveted through, and then we have the upper skin here with rivets here and here. So it gives a tab for connecting the two components. Now these rivets, obviously there's a criteria so they don't extend out from the fuselage. That would create too much friction. So they have to be embedded, and therefore they can only be so big. So you can have that shape here. So, and that's one of the reasons why they put a lot of them. And they needed to put one on each side for this design. So when we're talking about starting here from a plate that's 3.5 inch thick across, and then you end up, it's not to scale here, but it's only 1/8 of an inch. That's a lot of loss of material, and it's a very expensive process to go through in manufacturing. Titanium is difficult to machine. So as part of the optimization, again, the question was, can we make the same geometry but out of a casting? It would be awesome. You make the mold, you cast the titanium alloy, and you do some finishing. Fine, you can remachine some critical surfaces, like the outside here had to be really flat with a very specific radius shape, a curved shape, to maximize the aerodynamic. But really on the interior here, as long as it was strong enough, there wouldn't be a problem. I mean, you didn't need that many connections here. You needed the exterior shape. So if I go tomorrow and cast this to be a replacement, I'll make it a little bigger so I can machine the outside, and I will let the interior as cast if I can get the same properties out of it. And that, with respect to commercial aircraft, was a big deal. So we had to run all the standard tests. So we had some tensile tests to get the yield, the ultimate strength. We had fracture toughness tests. We talked about that KC in the last class. So that came in, and then we had some fatigue tests where you cycle a sample that has a crack in it, and you look at how fast it's growing over time. So we had all sorts of tests. So fatigue with a notch in it, without a notch in it. We had all that data. But in the end of the day, and that's what is very specific to the safety factor, you can have a casting factor of safety, which means that everything is nice, and I have this manufacturer that can make the mold. They pour the titanium under a very controlled environment, and they make these shapes that have great properties. But what if one day there's a piece of ceramic that takes off from the mold and gets embedded into the casting? Then everything we've done as far as property testing is off the map. The only way you can rely on a casting for this type of application, where a failure would be a big problem, was to do 100% inspection. So we could not assume that the casting was going to be right more than 100% of the time, to the second digit or third digit probability, it will work perfectly. And that was the biggest concern in dealing with a casting for a critical application. So even though we were looking at titanium, which, by the way, turns out titanium castings are very strong. They have very high fracture toughness, and they have very high casting properties. So they are a good candidate for replacement in an application like this. But then comes the reliability in manufacturing. And that's where that special inspection, it was a full through the thickness. They were going to do different non-destructive testing methods to be able to verify that there wasn't any little pieces from the mold that came into the pore. And the good news, though, by engineering, when you look at this, there's clearly going to be a side in tension and a side in compression. And the web, we can put holes in it, and it's still fine. So if you have a little impurity in the mold, it's okay. So you had essentially to verify that your top flange was going to have the properties you required. Having a little impurity on the compression side will not affect the buckling capacity, which is a controlling factor here. And same for the web. So there was only a small portion that really had to be 100% detail inspection to look for anomalies from the casting. And that was the way to get away from the casting factor of safety. Was something that Boeing had to use a lot in their design, and it was all there. And a lot of times was 1.25, but you could be higher also, depending. It really boils down to what is the application and what's the consequence of not getting it right on the inside of the part, because you can always have a visual criteria. They were also doing liquid penetrant testing on all of this, all the surfaces, whether it was tension or compression. But as far as looking at the inside, see if you had any impurities, that was really for the tension side. So it did work out, but it took a long time for the aircraft people to say, fine, we can fly with castings. And there were a lot of obstacles in the way. So for a small aviation company, most of it was looking at what the others were doing and justifying your decision based on what they were doing, as opposed to doing your full-blown research by yourself. So by the time that we found examples where people did the same thing, replacing an inspection after manufacturing for the casting factor of safety, that was becoming a lot easier after that to make the substitution. Now, there was still a part involved with actually making them and verifying in a full assembly that they would be equivalent. But that, I was gone by then. But so they couldn't just go and, yeah, put it on. So they still had to do a full-scale testing. Even though it's the same elastic properties, there was just no risk to take with respect to a component that was going to fit right in. And when you look at it, that's an example of substitution. Honestly, they didn't really know all the loads they could get on that component. They were looking in a stress analysis at different scenarios, combining them, but there was a little bit of a match with what happened in flight tests. They had gauges that would look at the stresses at locations they knew were going to be high stress locations from the design standpoint, from the computer analysis. Well, they still had to calibrate all that with an actual physical test. And the ultimate test before you could fly that wing, is they were attaching it to a fuselage and bending up and down about 3 feet. So that's about how much flexibility you get out of these wings. And you have to go back and forth a lot of times before something eventually let go. And then you have to figure out, is that okay? Was that something that we were planning on seeing let go at a certain point in time? But it was a displacement-based analysis. And they may have increased the displacement after you get more compliance out of it. But it's very severe testing, if you ask me, for an assembly to go through. But it was critical. If you start popping rivets in one specific location, now you go back and say, my analysis didn't predict that, so what did I do wrong? Because it's definitely happening now. So it's a good way for complex assemblies to really say, hey, we're giving this a shot. This is supposed to be a relatively optimized design. We take these other low points, and then you test it out and find out, is that really the case? There's another project I was working on at the same time, looking at the landing gear, where in those tests where they were just applying about twice the load that it will see at service, they had this crack growing really fast, and because of a torsional effect on one of the structural component that they never really analyzed for torsion. They did the tension, the bending on it, and they never really thought that torsion would become a dominant mode. So it was a good way to identify, not so early, because the problem then, they already had the weight of the aircraft sold for, and it was a very big, heavy steel component, and it was not strong enough. So they had to find, it became a very, it was a special team put on this task of replacing it with something hopefully of the same weight, or if not, then it goes to the accounting people for the weight of the aircraft. So if you take more weight there, now you need to take it out of somewhere else. So you got to be spending, it's an expensive process. You got to be spending money somewhere to maintain your overall baseline. And it becomes a negotiation. Well, I don't really want to change my design. I don't really want to change my design. But somebody has to give up some weight at the expense of cost. And the later it is in the design and that kind of business, it becomes very complicated. So we were very close to the end, and they were still fighting it between going to titanium, keeping up the steel, or with a different processing and a little stiffer, or just redesigning the whole thing. But you couldn't leave it as is. It was not an option. You knew you screwed up in a very specific loading mode that you didn't expect in a full assembly. So when you go back and say, well, we got to change the design of this, you can't say, oh, I'm going to go back and do a bending test on all these components and figuring out that they are equivalent, because you don't really know all the loading that's going to be applied on this. If you're looking at one of the ribs, it may very well be loaded here and here, or in a diagonal mode, and you'll have some bending, and maybe this is a zone of tension. How do I know? I haven't analyzed it in a full assembly. I've thought about it, I looked at the overall geometry, I have the wind pressure, the uplift, all of that. But what about everything else? So the torsion along the long axis is one of them. And it's also one that I didn't mention when we looked at the helicopter blade last week. So with a helicopter blade, you also have a torsion component that you need to take into account in your design. It needs to, so the tail part needs to be able to handle shear as well. And that's how you get shear stresses between your skin and the honeycomb in the back, just by trying to, the wing is trying to tear this. And there's only so much from a design standpoint that you want to allow for that torsional rotation, because otherwise you don't really get the attack angle you were designing for. So there's a lot that comes into every single piece. And when the wing effect, when the geometry becomes important, that's really where you have to think about strength, but you also have to think about keeping the shape and limiting the deflection to what's allowed. So it's very complex. You know, it all started with saying, oh, we want to be more critical of our processing so we can reduce our factor of safety to the same level than if we machine off that very thick component. But then in the process, you have to go through all the testing because you don't know exactly your loads again, and you're never going to load perfectly all the loads, at least not in anything that I worked on. So a lower end type of project. Oh, well, any question on that little rib structure? It was a very cool project. I was working in the office, and then the day came to go to the shop and actually start playing with these, and seeing how many pieces are involved, the different types of fasteners. You have all sorts of, and then you have to somehow deal with the different materials. You do have different materials here, and you have to be able to say, we've done it before, we never really had a corrosion issue with the interface or any fretting, any kind of corrosion type damage with the paint on. So the question that came, for example, is, can we take the paint off? We can save some money. Well, nobody really knew, because they started this saying, well, we're going to paint it. That's going to help for corrosion protection, but without really knowing if that was necessary. So it will come to you if you do any kind of design where you do it first, and then the second time around you try to shave off some of the extra safety that you had on the first place. And documentation can be helpful to the extent that sometimes if documentation says, well, we decided to do this because we knew we had to do something, and we thought about doing this, then the question comes to you is, now you have the history that there's no problem with this one, so it becomes a little harder to move to something else. See, if I take it off, now I need to look at other components, maybe within my company, or maybe somebody else did something that didn't have the coating, and did that work out? So to some extent, there are good things about being the first at doing something. So roof joist, so we're looking at a couple of things here. So we have the little joist, and then we have truss girders, or we could think of this as more like trusses. So they are holding multiple of these little joists. So the joist typical design is relatively simple. You have the top, you have a bottom, and you hold the pieces together with a bunch of diagonal. And sometime you may decide to put two diagonals up front, because that's really where you're going to have the highest amount of shear between top and bottom if these are simply supported. So it's just kind of basic structural engineering. This is not really so much part of the class, but just for your benefit, you end up with these few pieces at each end, if we have a simple support, that have a lot more load on them. And that's why if you go to a parking lot and they're doing an extension to a building, you may see these, and they'll have a different type of diagonal on the first member than what's going on after that. And it's not a guarantee, but what I have seen when we had snowstorms and all of this is if you didn't survive here, if these happen to be bad, then you will unzip the whole thing and have either the roof will sag or just come down altogether. But if we have very bad welding right in the middle, some of these are there with very limited loads on them. So they're there to keep the shape, but there's not a whole lot of stress because you don't have a lot of mismatch. So when I apply the displacement down here, what I'm doing is I'm stretching these, and they stretch differently, and that's why I get an overall extension and compression near the ends. in the middle, they're more or less staying together. It's like a sandwich. If you push on it, the two pieces of bread will slide with respect to each other at each end, but you'll stay together in the middle. That's kind of what's happening with a joist. Now, the way you design these is you have the dead weight. So this has a self weight. You're going to put a roof on it. We'll have some insulation, waterproofing, all sorts of things. That's easy to know. You can have a number for that. The snow load, the code has some very specific requirements for you. So if you are designing a roof as a structural engineer, I don't suggest you do it if you're not a structural engineer, but you have to go by very specific requirements for the location that you're building that roof for. And then if you have different heights, if this is a large warehouse like Costco, and you add an addition that has a different height, now you have to worry about the snow drift. So if you're going to pile up more snow, because now you have two elevations, you have to worry about whether you're close to the edge or in the middle. If you have a big mechanical system like a big air conditioning, that would also create some snow drift, and there are rules for all of it. So when we're talking about, say we're going to call this the demand here, well, it's very prescriptive. So you can go to the code and tell you, this is the load by square foot overall that you're putting on and that you have to design for. So as a designer, you can go and say, well, I'm going to play with the thickness here if I want to. I can play with the size of the members. I can put more diagonals at the beginning. A lot of it, I found out, was based on buckling and deflection. So if I come with the amount of steel that's on the joist and I join it properly, it will buckle before it fails. But from a manufacturing standpoint, when we come to capacities, people come to the assumption that I need a geometry that's right. And that means, say this is a compression diagonal here. This is tension. This is compression, just by the way it works out. If this is a compression, it's the size of it that I'm designing for. And a lot of time it would be, say, a round bar that's full, because it's cheaper to buy than to buying an empty tube that now is harder to weld at the connection or and cut. And so there are a lot of it that's based on cost. And when I come down to it, though, the reason I'm talking about this is the connections. What about the connections? They can't fail, because especially those that are in tension. And that's really an area where the manufacturer has to play a role, because there are some inspection criteria for the welds, but they're not perfectly respected by the people in the industry. So even though it's written something, when people go out, they don't necessarily do all these inspections all the time. And the question becomes, so what are we designing for? And what you'll see people doing for the critical connection is some people will come up with a design that's easier to inspect. Because if I'm asking somebody to make a weld that's difficult, and I can't really inspect it easily, it's a lot more risky of a design than if I tell them, do me a fillet weld. And we talked a bit about fillet weld. And I'm going to look at it, and as long as it's not too convex, we're good to go. Or it doesn't have too low of a contact angle. So that's the idea, that you have to, I would say it's more on the capacity side that there is judgment. I mean, all of us, anybody could, this is like an accounting process where the code tells you this, the code tells you that, the code tells you if you have this utility, just figure out what's your extra potential drift load based on this and this and that. So it's all going to be computerized. It's not perfect, but to some extent, it's consistent approach. What happens on the capacity side, and what I found out of 9 different collapses that I've looked at over about a 1-year period, there was only one job that they didn't have any welding issue. And it's not because you couldn't make these connections strong enough. They were just not built strong enough. Now, it doesn't mean that all the joists that people have low quality welds, because obviously I went on to what came down primarily. We did have some inspection on existing structures that were not under a distress. But when we talk about a failure in that specific industry, what I've seen is a lot of this. And then when it comes to the welds or the connections, to be a little bit more general, they didn't really know. Nobody could come and tell me, yeah, when we test this, it's got to be good for so much. It'd be like, well, there were stories of people just using a prying device to just test it out, see if it will and that's not to the same amount of load that you could have in service. It's just a way to figure out if your welding had some fusion. So talking about weld fusion, maybe the last thing. So these are some of the weld failures. So you see here that it's just breaking off. We're looking at this location, but from the underneath here. And the issue becomes, it shouldn't fail just like that, right at the interface between the angle of the joist and the welded bead. So you're looking at the welded bead here, and it's just splitting apart. And it was very common. That's a big warehouse for tomatoes, greenhouse, that I worked on. And same story where you look at this weld, and we talked a little bit about convexity. So maybe today you'd be able to say, if you go somewhere and you see this, oh, this looks like it's a little sort of deposited on the surface as opposed to being really weld fused. So it has a low contact angle here, and this is the same type of weld that after the fact you can see it just pull off from the surface of that cord, that structure, as opposed to ripping the metal apart with it. And we had some cross-section views of this. So you can see on this side the contact angle, it's actually, so it's between this location and this, it's less than 90 degrees. And you see the interface right here. So it's not fused. So this is the diagonal that has a little bent with a flat portion to be welded. And you have this lower chord of the joist. And right here, you have you have a little bit of grab here. But look, if you start cracking right here, it will pull right off. And on the other side, you have one here where the contact angle, so that's between this and this one, is probably 130 degrees here. So this is actually a very high quality fusion. And it penetrates here. So you see the line of the welded metal. If you don't have a good way to avoid a low fusion weld in, say, 1% of the time, you need to be able to live with the consequences of having one that fails. And that's where it comes in. So are you going to weld on both sides or just on one side? You could argue, I'm very unlucky if I get a bad weld on both sides. And I think it's less likely than getting it wrong just on one side. But if you weld just from one side, now your chances of a successful connection is going down, and you have a more complex loading because you have eccentricity. So if I take, and that's what they had here. So they had this weld connecting it here, off-centered from that rectangular tube, and they had no welds on the opposite side. You can see here, there's this little amount that's coming off here, the paint's coming off, and there was no weld further down the road on the other side of that round shape. So no redundancy and unknown capacity because it's a lot of welds. So how exactly are you going to go and inspect those? And in the other class, I talked a lot about why that weld is difficult to do. But the bottom idea is you're looking at a very heavy section. That's the diagonal that's coming down. And it's got to be welded to this rectangular tube, but the tube is thin. So you're looking at very different thicknesses of metals to be welded in a tight spot. So instead of having a fillet weld that's really just like this, and you make a nice bead, now you have to deal with it's on a round. So you have this empty root, and you're just trying to somehow deposit something in there. It's a lot harder weld to make than just at a corner. Your arc is bouncing up and down, so you have to be hitting with the arc. You need to be hitting one side or the other. So the way to do it that I've seen the most successful welder do it, they'll really weave their arc one side to the other, and they'll spend a little more time on this side than on this side. But you're becoming reliant on the expertise of your welder. And if you do so, you better have a program to make sure the guys really always do it consistently. And when you have somebody new coming to work, that they also qualify before they get into the production. And that's not always easy. So I think that's going to be it for the factors of safety for this semester. And I just want to wrap up very quickly. We talked about different factors of safety between industries. And we sort of trim it down to say, in reality, it's not that different. And the one that I was hitting on the most was the safety factor for the pressure vessel, where I pointed out, well, you have water hammers, you have other loads, you have welds that come into the design, and they're not really accounted for. They're not, you don't need to say, oh, I'm going to have maybe a water hammer. Everybody can have it. So it's part of the code, and it's built into that factor of safety of 4. We talked about demand and capacity in different industries, and I think you can see in some industry, the code, the Joist is a good example, will tell you this is the demand you designed for. And when you go to capacity, well, there's only so much you can do. If it's dependent on the ability of a welder, your strength depends on the quality of the welder, you will have more variability. So you need a factor of safety that's higher for that than if it's only going to be a bolted connection that you just have to make sure the bolt isn't with a knot. So it's the idea here when you look at capacity, what exactly, how difficult is your design to manufacture, and what kind of inspection are you going to enforce in practice? You can always say, yeah, inspect it, but is it really part of the contract, and are you going to check for it? Or are you just going to say, yeah, it's going to be a half-inch well of good quality, or whatever. Sometimes there's all sorts of email communication, do me this. Okay, well, good quality to me, I guess, is a little subjective, and that goes back to one of Professor Eager's lecture. If you can't quantify it, what's good, then how are you going to control it later? The probability of failure, we touched that again at the beginning, that there would be a different safety factor or a final acceptable safety factor for different types of structures. So I'm not going to rule that out. We can't say we're over-designing everything by 20%. It's not true. It will vary depending on how willing you are to risk a failure. And we had that popular shaft example that was designed to fail within 400 hours. And therefore, the safety factor for a 10-year life is less than 1. It's just the way it is. This one, I think, is what I'd like you to always keep in mind. You start with a factor of safety. So we build something together. We go and test it out here on Memorial Drive. And We come back, everything is fine, but as this product goes through a life, it may get beat up, in a certain area, get some scratches, and you do need to know that your factor of safety is going to come down. And therefore, depending how long you expect this to be in service, you have to start with, maybe you can start with a 1.2 safety factor. That's the popular shaft, more or less. Or the roof joist, you start with 2, and then the guys screw up the welding, and then you're close to 1, right from the get-go. You just don't know how likely it is that all of this will happen. But over time, your safety factor is going down. And it's not because you start with a safety factor of 3 that 2-3 years down the road you can say, oh yeah, you can put 20% more load on it. That's really what I want you to keep in mind, that when we do a bridge, it's not because it started with a safety factor of 2 that you can add 20% of construction load at any point in time on it. You don't know what the actual factor of safety is for this structure as it's being built a while ago, went through service, corrosion, everything you name it, the added lanes. Anything that can happen will happen sometimes. And it's all taking up that starting pie. If you start twice as strong, how much are you going to lose in manufacturing? Maybe you don't lose anything. That's your prototype. But in real manufacturing, some welds are not as good, so now you take out 50%. You just don't know. I think that's the bottom line. And the service history is another thing I hope you keep in mind. When something is being used a long time in the same way, it's safe. But how much of it you can modify it becomes the question, because you still don't have all the groundwork on where you stand with respect to demand and capacity. You're fine. Are you too good or just exactly where you should be? That it requires analysis. It's doable with those statistics thing that we talked about and looking at other designs. But it's not something you can say, oh yeah, we know it's designed with safety factor of 3 and we never had a failure, so we're going to add 20% load. I mean, you need more justification than just this idea that you have a large safety factor and therefore nobody wants to go to the calc again and see if we're still meeting code. Because you can modify if you're still within a history envelope like a code. It's when you go beyond that that you're more or less on your own. So I know you guys are going to be working on a specific standard, and Professor Eager is typically really good at keeping up with you. If there's something that's mechanically related, you can come to me. I have my email address on the website. And I'm at MIT quite a bit, so it's Belmar. Materials. My email address from MIT works now too, so you can use any of them. The one that's listed on the campus directory is working.